Hello all, this is Dr. Srilatha working as a Senior Assistant Professor in the Department of Mathematics in Vallurpalli Nageshwara VIGNANA JYOTHI Institute of Engineering and Technology, Hyderabad. So today I'm going to explain a brief about matrices. As you all know, starting from the lower classes up to intermediate, you all are familiar with the matrices. But when you enter into the engineering, you must very well known about the applications oriented. That means where you are learning this concept, you need to know where we are implementing. What are the future where we can implement this one here. So now coming to we'll see the real-time applications where matrices play a vital role in real-time scenarios. Now coming to the first application, that is matrices play a crucial role in weather prediction. That is to find the temperature and wind speed. Let me explain with one real-time scenario. Suppose meteorologists want to find the temperature and wind speed over a 3x3 or 4x4 grid over a region. So here region means you may take any small city or state. Let me explain that we are taking if we want to find out the temperature of our Hyderabad city, or we want to find out the temperature of Telangana state or Andhra state. So here we'll be finding the grids here. So here grid is nothing but each grid represents the location. So where we are implementing or where we are measuring the temperature and wind speed. So always matrices solve the system of differential equations to model and predict the climate and weather patterns. And they are used in simulations for wind flow, temperature distribution. And advanced forecasting relies on matrix computations for accuracy. Now next coming application is traffic flow analysis. So matrices play a vital role in traffic flow analysis in modeling, analyzing, and optimizing the movement of vehicles through road networks. So here matrices model and analyze the traffic patterns to optimize the signal timings and reduce the congestion. And it is used to calculate the shortest paths and predict the traffic patterns. So here transportation planners rely on matrices for efficient traffic management systems. So next application is cryptography. So here matrices play a vital role in cryptography, where in encoding and decoding the messages through matrix multiplication and matrix inverses. Here matrix encrypt the data into unreadable formats and decode it for secure communication. So in our day-to-day life, we know everyone is using WhatsApp chats. So whatever the information will be passing from one to another, it is of end-to-end encryption. And they are fundamental in modern and cryptographic techniques like Hill cipher and public key encryption, which ensures the data security in banking sector, e-commerce, and digital communication. So this is the format we'll be implementing here, that is A cross B. Let's take the original matrix as capital A and the coding matrix as capital B. The multiplication of this A cross B, which gives the encoding data in the matrix form. Another, the buzzword that is nowadays it is moving on, data science and ML. So here matrices are used to represent the data sets in the form of rows and columns, where each row represents the observation or the sample, or the column represents features. So this structured analysis makes it convenient to apply the mathematical operations and to convert this into matrices form with the help of the data sets. Another buzzword is machine learning. So what is this machine learning? Again, machine learning algorithms are totally based on the matrix applications. So here matrices will be serving as a fundamental in building blocks of all machine learning algorithms and data processing operations. Always these machine learning algorithms, not only in machine learning algorithms, but also in neural networks, where neural networks rely on matrix operations in modeling, optimization, and prediction process. Not only in artificial intelligence technologies, but also in image recognition and natural language processing. So here matrices represent the data sets and perform calculations like matrix multiplication in machine learning algorithms. And they are used in neural networks to process the inputs, weights, and biases for the predictions. So here matrices simply handling the large scale data in data science projects. Next coming application is econometrics. So here, as we all know, whenever we learn the matrices, first we'll be starting with the determinants, we'll be starting with the Kramer's rule. So here determinants and Kramer's plays a vital role in economics, where we are going to learn how it is useful for them in profit maximization or the loss minimization. So here economics models use matrices to analyze and interpret the large scale economic data, and they are applied in regression analysis. So what is this regression analysis? Depending on the past values, we will predict the future. So whatever the past it is, whether it is related to any company or the sector, whatever it is, we will predict the future. That is nothing but the forecasting and the optimization problem. So here matrices make handling multivariable data and relationships efficient. So just we took the 4 different categories here. That is 2 by 2 matrix we'll be getting here: excludable, non-excludable, rival, and non-rival. So whatever the categories they will be taking here in economics. So here we'll be getting 2 by 2 matrix. And similarly, when we're moving on to both economics and business here. So here input and output models in economics, we both mainly will use matrices to study the resource allocation and economic activity. So here matrices help to optimize the business operations like supply chains and financial forecasting. They provide insights into interdependencies within the economic systems. Now moving on to network analysis here. So just we are watching this graph here, some shortest path which we are having the edges and vertices. Now we are converting these edges and vertices into some matrix. We'll be calling this matrix is nothing but the adjacent matrix. So what is this adjacent matrix? Again, it is representation of both rows and columns. So here adjacent matrix represents the connections in social, transportation, and electrical networks. And they help in to analyze the patterns or to find the shortest paths and study the network centrality. So always matrices play a vital role in designing the efficient and scalable network systems. Now moving back on to signal processing. So here matrices handle the signal transformations and also in filtering and compression in audio, video, and communication systems. They are integral in algorithms like Fourier fast transforms, where this application includes the noise reduction, speech recognition, and image compression. Another example is structural analysis. So here matrices model forces, displacements, and stresses in structures like bridges, towers, and buildings. And it is used in finite element analysis to simulate the structural behavior under various conditions. So here, engineers use matrices to ensure the safety and optimize the designs. Another application is computer-aided design, which we'll be calling this as CAD. So matrices are used to design, scale, and manipulate the objects in engineering and architectural modeling, where this CAD software relies on matrices for three-dimensional rendering and the structural analysis, which ensures the accuracy and efficiency in creating the complex designs. So another application in our real-time sector is healthcare and medical imaging. As we all know, like the MRI scans or the CT scans or the X-rays, which represents the data, always will be allocating this in the form of, again, matrices to reconstruct the detailed images of the human body. So always matrices are used in reducing the noise and image enhancement for the better diagnosis. So here always matrices play a vital role in advancing the medical technology and also in patient care. So another application is ecology and population studies. So population matrices, so here model growth, it may be the growth rates, the migration, or the interaction between the species. And here it is used to study the ecosystems and predict the changes over the time period. So here always the matrices help ecologists to understand the dynamics of complex biological systems. So these are some real-time examples for matrices. So next, moving on to the basics of matrices, how to find rank of a matrix. Before finding the rank of a matrix, just we need to aware of some transformations. So next, moving on to next slide, that is elementary transformations. So here are the following operations on matrices we'll be calling. So here we'll be having two operations. One is row operation, another one is column operation. We'll be calling all these two operations are called elementary transformations. The first rule is we can interchange any two rows or any two columns. And the second rule is multiplying all elements of a row or column by a non-zero scalar. This is the second rule. And the third one is adding to the elements of a row or column to the corresponding elements of any row or column, and it is multiplied by a scalar. So these are the three transformations you need to keep in mind whenever we need to perform the row transformations as well as the column transformations. Now, just now I told about how to find rank of a matrix. Now we are having three different methods for finding the rank of a matrix. The first one is rank of a matrix by using minors, and second method is rank of a matrix by using echelon form, and the third one is rank of a matrix by using normal form. So before entering that, just we need to cope up with some properties here. So properties of rank of a matrix. The first one is rank of a matrix of capital A. Always it should be equal to order of non-singular matrix. And second property is rank of a matrix capital A should be equal to number of non-zero rows in echelon form of a matrix. And the third, rank of a matrix is less than order of singular matrix capital A. Rank of identity matrix is equal to order of the identity matrix. And the last property is rank of a null matrix is 0. So whenever we are doing the, or whenever we are finding the rank of a matrix, we need to keep in mind all these properties and the transformation rules we need to keep in mind. So by using the first method, now we can find the rank of a matrix here. So this is the first method, rank of a matrix by using minors. So first we'll able to know what are the steps for finding rank of a matrix using minors. The first step is we need to find the determinant of a matrix. And the second step is if the determinant matrix is not equal to 0, then in that case, the rank of a matrix is equal to order of the matrix. And the third property, that is the third one, is if the determinant matrix is equal to 0. So here directly we can't find the matrix here. If the determinant of the matrix is not equal to 0, in that case directly we'll be getting the rank as order of the matrix. If suppose this determinant is equal to 0, in that case we need to find the rank is equal to maximum of order of one of the minors, which is non-zero. So whenever we need to find the rank of a matrix by using minus method, you need to keep in mind all these three forms. Now we move on to how to find, we learn here how to find the rank of a matrix by using minors. So we need to find the given matrix here. This is the given matrix of order. I'm writing here 1, 5, 3, 9. So this is a matrix of order 2 by 2. If it is a matrix of order 2 by 2 means always we'll be denoting rank of a matrix as row of A. Since it is of order 2 by 2, always its rank should be, that is rank of A should be less than or equal to 2. Now consider second order minor. Consider second order minor. So what is our given matrix of order 2 by 2? 1, 5, 3, 9. So we know how to find the determinant of a matrix. Say when you're having the elements like A, B, C, D. So how to find the determinant for 2 by 2 matrix here? AD minus BC. So similarly we'll be implementing here 9 multiplied with 1, 9. And 5 multiplied with 3, that is 15. 9 minus 15, that is minus 6, which is equal to 6, that is not equal to 0. So there is a minor of order 2. There is a minor of order 2, which is not 0. Therefore, the rank of a matrix is equal to order of the matrix, that is we denote it as row of A. What is the order of this matrix here, which is equal to 2. Therefore, the rank of a matrix is equal to 2. Next, we move on to another one. So again, we are having 3 by 3 matrix here. So let's solve again by using minors. This is the given matrix capital A, which is of order 3 by 3, 5, 3, 0, 1, 2, minus 4, minus 2, minus 4, 8, which is of order 3 by 3. And what we need to keep in mind here, since it is of order 3, our rank should be less than or equal to 3. Now consider the third order minor. So third order minor means we need to find the determinant of order 3 by 3. So I'm writing here 5, 3, 0, 1, 2, minus 4, minus 2, minus 4, 8. So how to find this determinant here by using the signs? What are the signs we need to keep in mind here whenever we need to find the determinant here? So we're going to put it plus, minus, plus, alternatives here, signs here, minus, plus, minus, minus. Now coming to the first one here, we need to find the minor of this 5 here, except this row and this column. First put a sign of positive. So determinant, what is the minor here we'll be getting except that row and that column is 2, minus 4, 8. And next put the negative sign here. Again we need to find this minor, minus 3. Except this row and this column, what is the remaining elements we'll be having? 1, minus 2, minus 4, 8. And next we'll be having 0 here. No need to find that minor. So 5. What's the determinant here? 8 to 16. 16 minus 16. Minus 3. 8 minus 8, which is equal to 0. So since we got this determinant, that is the third order minor, I got it 0 here. That means the third order minor vanishes. So it vanishes means rank of A should be not equal to 3. That means you need to consider, since we got this third order minor is equal to 0. So the rank of A is not equal to 3. Now consider the second order minor. You may take any second order here. So just I am taking the first two elements, that is 5, 3, 1, 2. Now this is of order 2 by 2. Now find this determinant. Again this is in the form A, B, C, D, AD minus BC. 10 minus 3, which is equal to 7, and that is not equal to 0. So previously when we are finding the third order minor, where the determinant we got it 0. So we wrote that rank of A should be not equal to 3. So then we selected the minor of order 2 by 2. You may take any minor of any order which is of order 2 by 2. Now find this minor. Again we got it this minor as not equal to 0. That means there is a minor of order 2 which is not 0. Therefore, what is going to become here? The rank of a matrix is equal to disorder of the matrix 2, which is equal to 2. So like this we can calculate the matrices, finding the rank of a matrix by using minus. It might be of 2 by 2, it might be of 3 by 3, 3 by 4, whatever the order here. You need to follow these steps. Next, we may move on to the next one. So again, this is finding rank of a matrix by using minors. Again, we got the 3 by 3 matrix here. So given matrix, which is of order 0, minus 1, 5, 2, 4, minus 6, 1, 1, 5, which is of order 3 by 3. So if it is of order 3 by 3 means our rank should be less than or equal to 3. Now consider the third order minor. Third order minor. So 0, minus 1, 5, 2, 4. Just now we did how we did the second one. Again, you need to write the signs here. Since we got the first 0 here, next put minus. Minus of minus, this is plus 1. Except this row and this column, we write 2, 1, minus 6, 5. Next, plus 5 of, except this row and this column, 2, 4, 1, 1. Now find the determinants of this. 10 minus of minus, that is 10 plus 6. Plus 5. 2 minus 4, that is minus 2. So 16 minus 10, which is equal to 6. That is not equal to 0. So there is a minor of order 3, which is not 0. Therefore, what I can write here? The rank of a matrix, which is denoted by row of A. Since we got this 3 by 3 matrix, that is the order. Therefore, rank of A. The given matrix is going to become the order here. Now, the order of the matrix A is 3. So, these are the tips you need to keep in mind whenever you need to find the rank of a matrix by using minors. Thank you all for your patience and concentration.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.